welcome to the Bare Metal Cyber CISSP Prepcast. This series helps you prepare for the ISC² CISSP exam with focused explanations and practical context. In this episode, we are focusing on two foundational cryptographic concepts, hashing and message integrity. These topics are essential to understanding how modern systems detect tampering, verify the accuracy of data, and ensure that communications remain trustworthy from origin to destination. While encryption is often discussed in terms of confidentiality, hashing and integrity are about ensuring that data remains unchanged. Whether you are sending a software update, storing a log file, or processing a financial transaction, message integrity ensures that the information remains accurate and unaltered by unauthorized parties. Let's begin with hashing. Hashing is a cryptographic technique that transforms input data into a fixed-size string of characters, which is referred to as a hash value or message digest. This transformation is performed by a mathematical function. What makes hashing so powerful is its one-way nature. That means the original input cannot be feasibly reconstructed from the hash output. It also means that even a small change to the input data will produce a drastically different hash. This characteristic allows security professionals to detect even the tiniest modification to data. Several important properties define a strong cryptographic hash function. The first is determinism. The same input will always produce the same hash value. This is essential for integrity verification, where we compare an original hash with one calculated later from received data. The second property is efficiency. Hash functions must be able to process data quickly. This allows them to be used in high-performance environments like data transfer, authentication, and blockchain validation. Next is pre-management resistance. This means that given a hash value, it is computationally infeasible to reverse engineer the original input. In other words, even if an attacker sees a hash, they cannot determine what data created it. Finally, we have collision resistance. This means that it is extremely unlikely for two different inputs to produce the same hash value. A hash function with poor collision resistance may allow attackers to substitute malicious data without detection. Common hashing algorithms include SHA-256 and SHA-3, both of which belong to the secure hash algorithm family developed by the National Institute of Standards and Technology. These algorithms are currently considered secure and are widely used in digital signatures, certificate generation, and file verification. On the other hand, some older algorithms such as MD5 and SHA-1 are no longer recommended. These algorithms have known weaknesses that allow attackers to generate hash collisions, which undermines their ability to detect tampering. Despite being fast and easy to implement, their weaknesses render them unsuitable for modern security applications. Now let's turn our attention to message integrity. Message integrity ensures that data remains unchanged from the time it was sent or stored to the time it is received or accessed. Without message integrity, attackers could alter files, modify communications, or inject malicious code without detection. Integrity violations are serious. In financial systems, a single unauthorized modification could lead to fraud. In healthcare, altered records could result in incorrect diagnoses. In law enforcement or legal systems, tampered logs or evidence could undermine investigations. And in software development, inserting malicious code into updates or packages can compromise thousands of systems at once. To maintain message integrity, organizations use cryptographic tools such as hashes, digital signatures, and message authentication codes, or MACs. These tools allow recipients to verify whether data has been altered and whether the source is trustworthy. Hashing on its own verifies that the content has not changed. Digital signatures add the ability to authenticate the sender and prove that the data was signed using a private key. Message authentication codes combine hashing and symmetric encryption to ensure that a message came from a trusted party and was not altered during transmission. In practice, hashes are often attached to files, messages, or data packets. When the data is received, the system recalculates the hash and compares it to the original. If the values match, the data has not changed. If they differ, the data has been modified. either due to error or malicious intent. Let's now look at how to implement effective hashing and integrity practices. Organizations should begin by documenting clear policies for algorithm selection, integrity requirements, and implementation standards. These policies should align with current best practices and regulatory requirements. Strong hashing algorithms such as SHA-256 or SHA-3 should be used for all integrity operations. These algorithms provide reliable collision resistance and are approved by major standards bodies for use in secure systems. Hashes should accompany all sensitive files, transactions, and communications. For example, software vendors often publish hash values for their downloads. Users can verify these values before installation to ensure the software has not been tampered with. Email systems may use hashing to verify the content of messages, and secure logging systems use hashes to detect log tampering. Regular assessments are also essential. As with encryption, cryptographic algorithms used for integrity must be reviewed periodically to ensure they remain secure. If vulnerabilities are discovered or standards change, organizations must be prepared to update their systems accordingly. Training supports consistency. Staff must understand how hashes work, why they matter, and how to use them correctly. This includes development teams, system administrators, incident responders, and compliance personnel. For more cybersecurity content and books, please visit cybersecurity.me. You'll find bestseller books, training tools, and resources tailored specifically for cybersecurity professionals. You can also explore additional episodes and certification materials at baremetalcyber.com. Now, let's look at some specific security controls that support message integrity. First, digital signatures provide a robust method for ensuring authenticity and integrity. A digital signature is created by hashing a message and then encrypting the hash with the sender's private key. The recipient can then decrypt the signature with the sender's public key and compare the resulting hash with their own hash of the message. If the values match, the message is both authentic and unaltered. Digital signatures support non-repudiation, which means the sender cannot later deny having sent the message. This is critical in legal agreements, financial transactions, and software publishing. Another important tool is the message authentication code. Unlike digital signatures, which use asymmetric keys, MACs use symmetric keys. Both the sender and receiver must share the same key. The sender computes a MAC using the shared key and sends it, along with the message. The receiver then recomputes the MAC and compares it to the one received. If they match, the message is considered authentic and unchanged. Real-time integrity verification is also used in many systems. For example, file integrity monitoring tools constantly check the hashes of critical files and alert administrators if changes are detected. Secure logging systems use chained hashes to verify that log entries have not been altered or deleted. Audits play an important role. Regular audits should verify that hashing is being applied consistently, that digital signature processes are properly implemented, and that outdated algorithms are not in use. Incident response procedures should include specific steps for verifying data integrity. If tampering is suspected, investigators must verify whether hashes match, whether digital signatures are valid, and whether logs show signs of manipulation. Finally, let's explore how organizations maintain continuous improvement in hashing and integrity management. Start by reviewing policies and practices on a regular schedule. Stay informed about vulnerabilities in existing hash algorithms and watch for guidance from standards bodies like NIST. Conduct algorithm assessments and penetration tests that include data integrity scenarios. For example, simulate an integrity breach to see how well systems detect and respond. Review logging practices to ensure that they support tamper detection. Cross-functional collaboration is essential. Security teams must work closely with developers, system architects, auditors, and legal teams to ensure consistent application of hashing policies and to manage any legal or regulatory requirements involving data integrity. Training must be updated as new threats emerge and tools evolve. Integrity protection is only as effective as the people who manage it. Workshops, scenario-based exercises, and technical labs help reinforce secure practices and improve response readiness. Proactive strategies will always offer the strongest defense. These include adopting secure boot processes that verify system integrity at startup, deploying trusted computing modules to enforce hash validation, and using cloud-native tools to continuously monitor data integrity in distributed environments. Thank you for joining the CISSP Prepcast by Bare Metal Cyber. Visit baremetalcyber.com for additional episodes, comprehensive CISSP study resources, and personalized certification support. Deepen your understanding of hashing and message integrity, and will consistently support your journey towards CISSP certification success.